Hi everyone, in this part we're going to learn about the quantum mechanical model of the atom. The matter wave of the electron occupies a space near the nucleus and is continuously influenced by it. So if you consider this is your nucleus and then let's say you have one electron, so that electron is can be somewhere close to the nucleus and it's going to be continuously affected by the nucleus. Okay. The scientist named Schrödinger, he came up with a wave equation that would allow us to solve for the energy states associated with a particular atomic orbital. Normally, the Schrödinger wave equation or the Schrödinger wave function is given the symbol psi. And if you take the square of the Schrödinger equation, the square of the wave function gives the probability density. That means a measure of the probability of finding an electron of a particular energy in a particular region of the atom. Okay, like this. So this is after solving the Schrödinger wave equation, square of the Schrödinger wave function, that you can see hydrogen atom. So hydrogen atom, nucleus, you can see the nucleus is this little black dot right there. And then you can see lots of dots, blue dots surrounding the nucleus. Hydrogen atom has how many electrons? It has only one electron. But all these dots represent the places where the hydrogen electron can be because it's continuously moving. That is the probability of finding the electron around the nucleus. So this whole circle, wherever it ends spreading, is going to be the atomic volume of the hydrogen. And if you measure the distance from the center to the outer edge, that's going to be the radius of the hydrogen atom. Okay, and the electron takes the shape of a sphere where it exists in the most of the time. So because of that, we say the orbital, that the first electron in the hydrogen is occupy a spherical shape. Okay, so the first electron, it's in a first orbital that is spherical in shape, and this is the shape of that orbital. Okay. So now we're going to move on to find out the quantum numbers and atomic orbitals. So we normally use 3 quantum numbers to describe an atomic orbital, specified by 3 quantum numbers. You see 3 quantum numbers, and they are, the first one is called the principal quantum number, which is given the symbol n, which is a positive integer. The value n indicates the relative size of the orbital and therefore its relative distance from the nucleus. So it tells us the size and also how far it is from the nucleus. It also tells us about the energy of the electron. Okay, energy. And then the second quantum number is called the angular momentum quantum number, which gives us the symbol L. L is an integer. It can go from 0 to n minus 1. So the first one is n, which can be from 1 to 7 because we have 7 periods in the periodic table. And the angular momentum quantum number can be from 0 to n minus 1. The value L indicates the shape of the orbital. Okay, it tells us the shape of the orbital. For example, if you have n value as 1, what are the possible values for the L? L can be 0 to n minus 1. So if n equals 1, what are the possible values for L? Obviously it should be 0 first because it can go from 0 to n minus 1. If n equals 1, 1 minus 1 is 0. So the only possible value for L going to be 0, like that. Okay. And then the next one is the magnetic quantum number. That is going to be another integer which can take the values from minus L to plus L. Okay, minus L to plus L. If L equals 0, what are the possible values for ML? If you go from minus L to plus L, which is minus 0 to plus 0, which is going to be 0, right? So then the ML is going to be 0. Excuse me. So for the principal quantum number 1, L going to be 0, ML going to be 0, like that. Okay. And we can look at some examples. So let's see principal quantum number. Let's take the principal quantum number as n equals 1. And then we can find out what are the possible L values. Remember, L can take 0 to n minus 1. So if n equals 1, what are the possible L values? 0 to n minus 1, 0 should be there, right? And then the ML going to be minus L to plus L, correct? So then the ML is going to be 0 minus L, because L is 0. And if you take the second principal quantum number 2, if n equals 2, what's happening? What are the possible L values? It can also go from 0 to n minus 1. So 0 is there, and then n minus 1, n is going to be 2, 2 minus 1 is 1. So there are two possible values if the principal quantum number is 2. Two possible L values are 0 and 1. Okay, and then what about ML? Always if L equals 0, ML going to be 0, minus L to plus L. And then what about ML values if you have L equals 1? Going from minus L to plus L, meaning minus 1 to plus 1. So that's going to be minus 1. And when we are going from minus 1 to plus 1, remember it has to go through 0. 0 plus 1. So there are three possible values. Minus 1, 0, plus 1. Okay. And if the principal quantum number 3, n equals 3, what are the possible L values? You can have 0, because it goes from 0 to n minus 1. 0 to n minus 1. n minus 1, 3 minus 1 would be 2. So then 0 to 2. You will have 0, 1, 2. 3 L values. Okay. And then what are the possible ML values? Again for the 0, minus L to plus L, that's going to be 0. And if it is 1, L equals 1, minus L to plus L would be minus 1, 0, plus 1. And then ML values for the 2 would be minus 2, minus 1, 0, plus 1 and plus 2. Okay. That's the third principal quantum number. And if you go to the fourth one, we can also do the same thing for the fourth one. I'm going to go ahead and insert another slide over here. Okay, so let's see if you want to do n equals 4. So n equals 4. And what are the possible L values? Remember, L can go from 0 to n minus 1. So it has 0, 1, 2, 3. Because L is 0 to n minus 1. n minus 1 would be 4. So 0, 1, 2, 3. And then if you go to ML values for these ones, ML going to be minus L to plus L. So this would be 0. And for the 1, it would be minus 1, 0, plus 1. And then for L equals 2, it would be minus 2, minus 1, 0, plus 1, plus 2. right? And ml values for L equals 3 would be minus 3, minus 2, minus 1, 0, and then you have plus 1, plus 2, plus 3. So how many different orbitals? So all of these represent the number of orbitals. So n gives you the principal quantum number, L will tell you the shape of the orbital, and ml is for the orientation. ml is orientation. So in the principal quantum number 1, you have only one orientation, one ml value, meaning there's only one orbital. That's going to be your s orbital. Now again, so these L values, they represent the shape of the orbital. Whenever the L value is 0, that tells you that is a s orbital. Okay, so even for the second principal quantum number, 0 means s orbital. So this is s orbital. Whenever L equals 0, that's going to be your s orbital. And then when the L value is 1, that's a p orbital. And this is again a p orbital. If the L equals 2, that's going to be a d orbital. So in the principal quantum number 1, we have only one s orbital. In the principal quantum number 2, we have s and p. Principal quantum number 3, you have s, p and d. And then if you go to the fourth one, the fourth principal quantum number, you have s orbital, L equals 0. And then you have p orbital, L equals 1. D orbital, L equals 2. And f orbital, L equals 3. Okay, so this 0, 1, 2, 3 L values represent the shapes of the orbital S, P, D, F. So you kind of have to remember that. When the L value is 0, it's S, 1, P, 2, D, 3, F. And these ML values that we talk about, it talks about the orientation, also meaning the number of orbitals that we have in one particular shape. Since ML has only one value, which is 0, so you can have only one s orbital. And for the p orbital, there are three orientations, minus 1, 0, plus 1. Meaning there are three possible orbitals for p orbital. And for the d, you have 5 ml values. Minus 2, minus 1, 0, plus 1, plus 2. So that gives you 5d orbitals. So there are 5d orbitals possible. And if it is f orbital, you have 7 ml values, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, meaning there are 7 possible f orbitals are there. Okay, same thing over here. In the principal quantum number 1, you can have only one of the s orbitals. Principal quantum number 2, you can have again one of the s orbitals. And how many p orbitals? 1, 2, 3. There are 3 p orbitals. That's in the principal quantum number 2. And if you look at principal quantum number 3, what do we have? We have s, p and d. So one of the s orbitals, and then you have 3 of the p orbitals and 5 of the d orbitals. Okay? And you can see 1, 2, 3, 4. Of all the 4 principal quantum numbers, you have s orbitals. So we should be able to differentiate these s orbitals. How do we differentiate? We label them as designation as a sub orbital. Okay, so this one we're going to name it as a 1s orbital. If it is happen to be in the second orbital, we call it as a 2s orbital. If it is in the third one, that's going to be 3s orbital. But we have only one s orbital, one type. But 1s, 2s, 3s represent which principal quantum number it exists. Similarly, we can do for the p orbital. This is 2p orbital and this is 3p orbital. Meaning that's the principal quantum number that orbital exists. And then the d, this d orbital starts in the third principal quantum number. So we call it as a 3d orbital. And similarly, all the orbitals in the fourth principal quantum number, we're going to designate them as 4s, 4p, 4d, 4f, like that. Okay. Any question? Oh well, how would you let me know if you have any questions? Yes, feel free to contact me. Okay. So hierarchy of quantum numbers for atomic orbitals. So this is the same thing as a summary what we just talked about. So the name, principal quantum number, and then you have angular momentum, and then the magnetic quantum number. Okay. Okay, so the principal quantum number could be positive integer 1, 2, 3. You can have 1, 2, 3 principal quantum number. And then the angular momentum quantum number, which tells us about the shape of the orbital, given the symbol L, could be 0 to n minus 1. So when it is 1, it will be only 1, 0. 1 minus 1 would also be 0. Okay. And if the principal quantum number is 2, you can have two L values, 0 to n minus 1. 2 minus 1 is 1. So 0 and 1. And if the principal quantum number 3, your L values are going to be 0, 1 and 2. So that tells us about the shapes of the orbital. When it is 0, shape is S. When it is 1, shape is P. So in the third level, we have S, P and D. Okay. And then the magnetic quantum number, which tells us the orientation of the orbital, can go from minus L to plus L, and in the middle you have 0. If L is 0, you have only one value. If L is 1, can go from minus 1, 0, plus 1. So there are 3 possible p orbitals. And when the L equals 2, it has minus 2, minus 1, 0, plus 1, plus 2. So there are 5 possible d orbitals. So in the principal quantum number 3, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 possible orbitals. We have 1 of the S, we have 3p, and we have 5 d orbitals. Okay. So here's another chart summarizing everything, the same thing that we talked about. So you can see the principal quantum numbers 1, 2, 3, 4, and then the possible L values 0, 0 and 1, 0, 1, 2, 0, 1, 2, 3, 3, and then the sub-level designations 1s, 2s and 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay. So the number that come prior to the orbital shape tells us which one is the principal quantum number. 1, 2, 3, 4 that represent principal quantum number. And then you have ML values that tells us about the orientation. So for the S orbital, spherical in shape, it has only one orientation. It exists only in one direction, only one axis. And then if you have a p orbital, you can see there are 3 orientations, 1, 2, 3, meaning number of orbitals in that sub-level is 3. 1, 2, 3. Also, it could be 2L plus 1. 2 times 1, 2 plus 1, right? And then likewise in the third principal quantum number, you have S orbital, it has only one orbital. If you have p, that's going to be 1, 2, 3 p orbitals, and 1, 2, 3, 4, 5 would be d orbitals. The total number would be 9. In the principal quantum number 4, there's only going to be one s orbital, there's going to be 3 p orbitals, there's going to be 5 d orbitals, and then there's going to be 7 f orbital. So the maximum number of orbitals is going to be 16 in this fourth principal quantum number. Okay. So I'm going to go ahead and finish this section, and then in the next video I will explain you about the problems so that we can work it together. Okay. Bye-bye for now.